some homework questions.
Yeah, Vesper is related to hybridization, basically. The sequence goes, we go Lewis structures, and then Vesper, and then hybridization, and valence bond theory. It's all part of valence bond theory, Vesper. And so we use Vesper to predict the three-dimensional shapes based on valence bond theory repulsions. And so was there like a specific question that was?
I'd have to find it, but it was just a question about like definitions of like Vesper, valence bond, like all of that.
Mm-hmm. We could take a look at this. Would you like
This is a chem study, though.
Well, the chem study I was looking for is missing, but this is an older one. This is talking about shapes, so this would be Vesper. Let me see. We'll take a look at this video since we have time. Yeah, the normal angles don't work. The S is okay because the S you can bond anywhere on the sphere, and so there's no angle associated with that. But the p orbitals are going to have 90-degree angles, so it's impossible that you're going to have, let's say, a tetrahedral structure utilizing the normal atomic orbitals, and so you're stuck there. What do you do in that particular case? Well, what was done is afterwards they figured out, well, how are you going to get orbitals at 109 angles? How are you going to get orbitals at 180 angles? There are no orbitals at 180 angles. And so from quantum mechanics and the hydrogen atom, and we assume that all the other elements have hydrogen-like orbitals. And so we know the orbitals for the hydrogen atoms exactly because the Schrodinger equation can be solved for hydrogen. But all the other elements there, we start off with the assumption that the orbitals are going to be similar to the hydrogen orbitals. And so they're all going to have the SPD. And in fact, the whole periodic table is arranged with those orbitals. However, none of those orbitals work in bonding. And so afterwards, it was modified to incorporate this. And so the calculations were actually done for this. We even mixed the atomic orbitals using quantum mechanics. And then, so it's quantum mechanics up to a point, and so you're mixing the orbitals, and then you're doing the overlap. Okay, so that's a major simplification of that. We can mix the orbitals at different levels, though. Really what we should do is we should just, at least for the valence orbitals, we should do an LCAO, which is a linear combination rather than, which forms molecular orbitals rather than a combination of atomic orbitals to form new hybrid atomic orbitals. So the hybrid orbitals did not come first. The Vesper came first, and then experiment shows that the angles are off from what we could use, and therefore you have to come up with some fix for that, and that was the fix, is hybridized orbitals, hybridized atomic orbitals. Now you could take hybridized atomic orbitals and do a linear combination of atomic orbitals to get molecular orbitals based on hybrid atomic orbitals as well. And so this is sequence. And so a valence bond takes it up to a certain point and then stops looking at the overlap, and the molecular orbital takes it to another level entirely, much higher level. But if you're interested, are you interested in seeing more about Vesper, or?
Yeah.
Yeah, all right. We'll take a look at Vesper. I was going to show another video about X-ray crystallography, but they didn't put it, unfortunately, on their site. This is from Berkeley. Continue with this. So we got to get through today's lab. We're going to look at bonding in solids. So bonding in solids, we have different solids, and one of the ways we characterize solids is by the bonding. if the bonding is due to IMFs, you know, we'll just look at the major IMFs here, which would be dispersion, dipole, or dispersion and dipole, and hydrogen bonds. So we could have combinations. And so dispersion is between nonpolar species. And so these are typically weak unless you're looking at asphalt. And so we could say they vary from weak to strong. An example of weak would be like solid methane. If we look at solid methane, the methane are like little balls. They're tetrahedral in shape, and so they have this spherical symmetry. And so it's packing together a whole bunch of these balls here. And what holds all these balls together? What holds all these balls together are just instantaneous dipole, induced dipole. Because even if these bonds are polar, this whole thing's going to be nonpolar because of its tetrahedral symmetry, spherical symmetry. And so if we did have bond dipoles here, they all cancel out. We do have bond dipoles, but the bond dipoles are so small that all hydrocarbons, no matter what the shape is, are nonpolar. And so you could have really complicated shapes of hydrocarbons, but it's still going to be nonpolar, even if the bond dipoles wouldn't cancel out because the bond dipoles are negligible. And so this is going to have weak dispersion forces. What else would have weak dispersion forces? Other things would be like solid helium. I'm not going in this order here. Solid argon. You know, helium, you have to get it awfully cold to freeze it because the forces are so weak. Argon, hydrogen, dry ice, CO2, carbon tetrachloride, etc. Strong would be like asphalt. Asphalt is a mixture of big hydrocarbons. So let's take a look. But as far as strength goes, it's still weak. Try that again. So this is from Botanica. Asphalt consists of compounds of hydrogen carbon, so hydrocarbons, with minor portions of other impurities, nitrogen, sulfur, oxygen. The thing that differentiates these are these, they have very, very long chains. And so, typically, and they're mixtures, so different things. So that's asphalt. We could have long chain or branched chains. And so carbon can form these long, actually there's zigzag chains if we do it because they're all pretty much sp3. So we wouldn't have 180 angles here, but just to save space, we'll do this. And then we'll have hydrogens filling it out. And just because of its sheer number of electrons, you know, that's what holds them together. And so we get these very big molecules. Some people say these big molecules are heavy, but you know, a single molecule of asphalt doesn't weigh much. You know, a single asphalt molecule would be much lighter than a piece of dust. a piece of dust that might be picked up by a small breeze and blown into the air. And so what holds these together are dispersion type forces. So strong, this is relative, because asphalt you can still melt, at reasonable temperature, but some things are very hard to melt. And usually what we do to get an idea of how strongly bonded these things are is by it melting. So that's dispersion. And then we have dipole. Examples of dipole would be like solid chloroform, solid HCl, solid what's that? Dimethyl ether. Most of these are liquid, so dipole would be like this: CH3O, CH3. It's not linear like this. It would be bent. These two lone pairs here. But typically dipole, these are going to have very low melting points as well. And then we have H bonds. And so we have dispersion, dipole, and H bonds. H bonds would be like, if we have a lot of them, it could be quite strong. It could be like molasses, we're talking, or water. Hydrogen bonding interactions. Water melts at 0 degrees C. So, in general, all these molecular solids, molecular solids are going to be held together by IMFs. So all these molecular solids are going to be soft and low to moderate melting points. And they're going to be soluble. So for example, the nonpolar ones are going to be soluble in nonpolar. We have the solubility rules. Like dissolves like. So if we have nonpolar, if you want to dissolve asphalt, then use a nonpolar solvent like benzene, something like that. And then you should be able to dissolve the asphalt. You aren't going to be able to dissolve asphalt in water because water is quite polar. However, if you have dipole or H bonding substances, then these will dissolve in polar solvents like water, etc. Okay, so molecular solids, what's holding the molecules together are IMFs. Okay, next we're going to look at metallic solids. Let me talk about this. Typically, one other thing is the bonding is not really directional. Like here it's somewhat directional. In ice, the ice molecules like to optimize the hydrogen bonding, so it's quite directional. But in some of these others, like solid methane, it's not really. It depends on how you pack the molecules. Okay, when we go to metallic are also fairly non-directional. Metallic are going to be held by metallic bonds. Metallic bonds vary from weak. Weak would be like cesium, to quite strong. Strong would be like iridium, gold, it's pretty strongly bonded, platinum. These have, this cesium has a melting point around room temperature. These have very high melting points. So for example, platinum melts at 1600 degrees Celsius, over 2000 Fahrenheit. And so these are hard to melt. That means they're fairly strongly bonded. In Chem 1B, we'll talk about the bonding a little more. Because the interesting thing is it seems to be correlated with the number of d electrons. So if we're looking at the d block here, the melting point seems to peak in the middle of the d block. It goes. And so it seems to be correlated with the more unpaired electrons here, the better. This would be the melting point curve here. So things that kind of in the center of the d block have very high melting points. And over on the left and the right, a little lower. The bonding is, what I mean by bonding is fairly non-directional. The bonding in, let's say, something like gold is fairly delocalized. We have the valence electrons are delocalized here and not localized in a specific orbital. And so typically what we do with gold is we just try to pack as many golds together. You know what this is called? If you look at the center gold atom here, this is called closest packing. In closest packing, we have one gold atom in the middle of how many other gold atoms can we fit around it? 6. And then how many can we put on top that will be in contact with this? What is the maximum number you think I can get to touch this center gold atom? 4? 4 is close. It turns out it's 3. So do you see this little dip here? That gap? I'll put one there, one in this little gap here, and one in this little gap here. And so now I have 9 gold atoms there. And so this is on the top, and then underneath, how many gold atoms can I put in contact with that center one? 3 more. Now I have a choice which little gaps I can fill. But what I'm going to do is I'm going to use the opposite. These little gaps are called holes. And those holes, I'm going to use this hole here. And this one here. And this one here. So this gold atom has how many other gold atoms bonded to it? 12. We call this closest packing of atoms. And so if you're going to pack something together, you want to pack it together as closely and as tightly as possible. And so this would be solid gold here. Now, what is the hybridization for solid gold? If we have 12 bonds to it, what do we call it? Should we call it, when we normally do hybridization, we do S, P, 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 that's 4 orbitals, D, 5 orbitals. How many orbitals are we going to need? We're going to need 12 orbitals. D, 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 well, I just ran out of D's. Where do I go next? F, 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 F. SP3, D10, F2? Is that what we should do for hybridization? No. No, we don't do that for metals. In fact, metals, the best way to describe, this is where valence bond theory fails. Valence bond theory does have a number of failures. I didn't talk about all of them. One of them is for metals like this, valence bond theory fails. Another one is for complexes. I talked about complexes yesterday. Valence bond theory fails for describing the bonding in complexes. In fact, I just was reading about one complex, that showed some promise. Let's see if I could bring that article up. Now, obviously, you want to know the bonding of this quite well. This is just a recent article I just saw. But this is really interesting because there's, Teflon. Teflon is one of these forever wastes. It consists of polyfluorinated hydrocarbons, in which you take a hydrocarbon and you remove all the hydrogens. And then you replace the hydrogens with fluorines. And the fluorines are strongly bonded to it, and so it makes it really tough material, really hard to react. And so it's semi-inert, and so they call these like forever. And one of these classes is these PFAS, polyfluorinated alkyl ones. But this magnesium complex appears to pluck fluorine from these, and if you can pluck the fluorines away, then it becomes a lot more reactive. So this was a really interesting article. This just came out May 18th. And so here's the complex here. It has this magnesium stuck here. How do you describe the bonding in this? Well, we don't use valence bond theory to describe bonding in complexes. We use MO theory because valence bond theory just doesn't work. And here it has plucked off 2 fluorines off the chain. And so they're looking at this for PTFE, polytetrafluoroethylene. It's Teflon, basically. And they're looking at this for per and polyfluoroalkyl substances, PFAS. And so these forever chemicals that they want to ban, people are looking at ways to recycle them to make them useful. But anyway, we use MO theory, and this is a complex. This is just metal. And so for something like this, we use band theory, which is MO theory applied to solids. But here we have 12. Now the bonding's not directional. What is the shape? What do you call it? Is that octahedral? No, it's not octahedral. Do you have a name for this shape? No, we don't have a name for this, as a polygon. We do have another name. This is called CCP, which I'm going to talk about today. And we're going to build a model of CCP. You know what CCP stands for? CP stands for closest packing. So this is closest packing. And C, the first C stands for cubic. Cubic stands for, do you see the 3 on the bottom and the 3 on top are flipped 180? And so that's cubic. If I made the 3 on the bottom superimposed with the 3 on the top, that's called hexagonal. And so we have different names. This is called cubic closest packing. So that's what we named this. Now with cubic closest packing, the bonding is not so directional. What are the bond angles? The bond angles aren't so critical because, if you just move it a little bit, it doesn't break the bond. So if we just displace this, it's going to change the density a little bit, but if we displace this a little bit, it doesn't break the bond. So we can move these a little bit. Versus other things, if I tried to move the hydrogen too much, it's going to break the bond in water. And so it's fairly non-directional bonding. And so one of the properties is, number 1, very high melting point for this. Okay? And it also is going to have other properties too. Good electrical conduction because we have delocalized, the molecular orbitals are delocalized over the entire structure. And we have these bands of molecular orbitals. And we have something called the conduction band and the valence band. And the electrons are free to move in the conduction band. So it's electron C model of we had talked about before. But anyway, good electrical conduction, good thermal conduction. The thermal conduction can be through vibrations and also through the motion of electrons. So we have excellent thermal conductivity, excellent electrical conductivity. They're malleable, that is, you can distort the structure without breaking the bonds. They're ductile, you can draw these into thin wire. And at least for gold, it has a high melting point. Okay, so looking at metallic, hardness. Actually, hardness. Is gold very hard? No. It's not very hard. I forgot to talk about. Molecular compounds are soft, all of them. Like ice. Ice is soft. A hardness varies from soft to very hard. Tungsten's quite hard. There are some hard metals that are more brittle that have a different structure. And they have a more directional structure, so it can make them quite brittle and hard. So hardness varies from soft to very hard. Melting point varies from low to very high. They have a luster. They're ductile, malleable, very good conductors of heat and electricity. So some examples. Sodium is weakly bonded. The alkali metals, the alkaline earths are weak. Aluminum's pretty decent. Iron, tin, copper is good. Silver is good. Tungsten's good. And so this is varying from soft to hard and low melting to high melting here. All right, that's metallic. And then we're going to look at something that has much more directional bonding. And that would be network covalent, which is going to be next. If we look at how the gold atoms are arranged here, versus a network covalent would consist of covalent bonds rather than metallic bonds. Covalent bonds are fairly strong. So covalent bonds, an example would be, let's say, carbon solid in the form of diamond. So if we look at diamond, diamond consists of all sp3 carbons. And then each of these carbons is sp3. And then we build up an sp3 network of carbons. So is diamond very malleable or ductile? No. As if we try to bend the angle here of one of the carbons, so this would be diamond. If we tried to bend the angle, the optimum angle here is 109. So if I try to push it more, 107, 106, 101, eventually the overlap is going to get poor. We want a direct overlap of the atomic orbitals. So these are sp3 sigma bonds. And to optimize an sp3 sigma bond, we need them to go straight in like this. And so we get good orbital overlap. This is valence bond theory. We can also describe diamond in terms of molecular orbital theory and band theory as well. But here it's probably easiest. So now if I try to push this oxygen here, down, 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 the orbitals are going to kink. And when they kink, there's not good overlap. It's going to weaken the bond tremendously. And so diamond is going to break, whereas gold will not break. Gold will just deform. You can't deform the diamond. Break. And so this is a highly directional bonding. This is not highly directional bonding. So there's a big difference. And so these are sp3. All the carbons are sp3. Graphite, on the other hand, consists of all sp2. Graphite's a combination of network covalent and molecular. And so when we look at graphite, graphite contains these sheets of sp2 carbons. And we get these two-dimensional sheets. Graphite is an excellent conductor of electricity in the two-dimensional sheet. This is what's called an anisotropic conductor because of the p orbitals. All the p orbitals are overlapping. And so we have complete delocalization. This is valence bond theory again. Valence bond theory works quite nicely here, or we could use MO theory. But if we look at it, all the pi electrons are delocalized over the entire sheet. And so graphite has excellent electrical conductivity within the sheet. However, it has very poor conductivity between sheets. So I have one sheet here, the next sheet will stack right on top of this one. And I'm not going to get any conduction because the electron would have to jump from one sheet to the next sheet. It would require very high voltage to do that. And so what we say about graphite is an anisotropic conductor, whereas gold is an isotropic conductor. Gold conducts in 3 dimensions quite well, but graphite only conducts in 2 dimensions. It also conducts heat by the kinetic energy of the electrons in 2 dimensions, but it doesn't conduct it perpendicular to the sheet. And so it's a good insulator between the sheets. So the sheets just stack on top. The sheets are held together just by molecular, that is, dispersion forces. You know, those are like benzene rings. Yeah. So here we can see it. It's an image. Of graphite. Here's 3 sheets of graphite, and they show the relative orientation of the sheets, how they line up. And the gap is 335 picometers between the sheets. The bond, the carbon-carbon bond, is 142 picometers in length. And so there's this gap here. These sheets slide easily one on top of each other. So graphite's used as a high temperature and high pressure lubricant. High temperature because it's hard to break these carbon-carbon bonds. You know, they're fairly strong. High pressure because these sheets can withstand enormous pressure. And so these are used in high temperature, high pressure scenarios. But you know, you can buy graphite for your door hinges and locks, whatever. It's a pretty good lubricant. Let's see, diamond. This is diamond structure in here as well. These are other allotropes. These are molecular forms of carbon. The buckyballs. These are spheres formed by carbon. This is a bucky tube or nanotube. These carbon atoms as well. These are going to be held together by dispersion forces. So they'll be very soft. Diamond and graphite are fairly hard materials. Diamond's especially hard. Do you know the hardness of diamond? Bonds are strong. Bonds are highly directional. And so it makes this a very hard material. Diamond has a hardness of 10. 10 used to be the highest. Diamond was the hardest material, but now there are materials that are harder than diamond. Okay, that's network covalent. Another one is quartz. Quartz is also very hard, not as hard as diamond. But quartz is going to consist of sp3 silicons. The oxygens are also sp3. But rather than having all carbon atoms here, we'll have a silicon in the center of a tetrahedron of oxygens. And like diamond, it extends in 3 dimensions. So we just extend this out to be quartz. quartz is going to be sp3 sigma bonds here, so it's very directional bonding. And the bonds are fairly strong. All right, the next and the last type will be ionic. And we're going to spend some time looking at ionic solids. Also the diamond structure. We'll build the diamond structure too for today's lab. But ionic solids are going to be held by ionic bonds. And these are going to be hard as well, and moderate to high melting points. Network covalent most are very hard and very high melting points. The network covalent are very strong. But ionic can also be very strong. It depends on how strong the ionic bond is. Ionic bond can be fairly weak, like in cesium iodide. Cesium iodide solid would be pretty weak ionic bond because they're big ions. Whereas aluminum oxide would be extremely strong. So this is on the weaker end of the spectrum. This is on the stronger end of the spectrum. Aluminum oxide is extremely tough and fairly inert because the bonds are so strong. And so aluminum oxide has an extreme melting point. So, you know, if you have a platinum oven, which I did, I had a platinum oven that I was using in the lab. Platinum oven goes up to 1600 degrees Celsius. So what types of stuff do you put in there? You know, if you put in porcelain or glazed porcelain, you're going to melt the glaze of the porcelain. And so if you put, let's say, other ceramics, you're gonna have problems. And so I had a whole bunch of aluminum oxide cookware, you know, aluminum oxide boats, aluminum oxide beakers, aluminum oxide. It's all this stuff because if you put glass in there, for sure it's going to melt. And quartz glass is pretty high though. The quartz glass melts at around 1,000, or softens, I should say, around 1,000. But that's not high enough. Okay, so anyway, we are going to have moderate to very high melting points for this. And these are brittle, they're hard and brittle. However, we can cleave them quite easily. So they're susceptible to cleavage. That is, if we try to displace it, they break quite easily. That's what leads to the brittleness. They break quite easily because right now, if we look at cesium iodide, we're going to have a lattice like this. And so if we push one side of the lattice down, let's say we push this side of the lattice down, then displacing this anion down one position will mean the negative and negative. Negative and negative is going to repel. And this displacing down one position will mean a positive positive. And so all you have to do is apply a little bit of force to displace this, and then it cleaves. It breaks off easily. And so that's one characteristic. Here it's going to just fracture and fracture. All right, so that's some bonding in the solids and some properties that are associated with the bonding in the solids. What we're going to do is we're going to look at the structure of the solids next. Not all solids form nice ordered arrangements of atoms. We have two types of structures. We have amorphous and crystalline. Amorphous is like a frozen liquid. You know, there's some randomness to it, in which you could freeze the position of the atoms or the molecules in place, like a rapid freeze. In fact, that's how you form a lot of amorphous things. You don't give it enough time to optimize. the bonding interaction, and so you freeze it extremely fast. So things are a little bit disorganized. For crystalline, everything's organized, and so this is an organized structure. In other words, for amorphous, we say that there is no long range order, or LRO. Crystalline solids have to have long range order. So for an amorphous solid, it's hard to predict, like let's say 300 angstroms down the road, what atom's going to be there. But in the crystalline solid, we can say in 300 angstroms, we expect this. This is like a brick wall. This would be like in each brick we call it a unit cell. So there's an ordered arrangement of these unit cells here. Whereas here we're going to have some distortions. You know, some of the bricks were kind of offset, and things got a little bit disordered. All right, so let's, oh, here's diamond. This is the diamond structure in which we have sp3 carbons. This is one of the bricks that make up the crystalline structure. This brick is called a unit cell. And we can take this unit cell and just repeat it. And so when you look at this unit cell, there are certain things that we look for in a unit cell for this. And so we're going to build this one here so we can look at it directly. And so to build these, we're going to check out a model kit. You can work with others or you can work solo. But go ahead and go to the stock room. You're going to get one of these guys here. Look at building some of these.
Yes, sir.
Let me just say something here. In this equation, I used A. I could have used R, you know. Just substitute. We know what A is in terms of R. So I could have used this in A or R, doesn't matter, for packing efficiency. The same thing with density. I could do it in either terms of A or R. A is the length of the unit cell. You get the theoretical density. This is a very quick calculation. Density is just mass divided by the volume. Now, is it the density of the atom or the density of solid polonium? If it's the density of the atom, then the volume is the volume of the sphere. But we're not talking about the density of the atom. We're talking about the density of solid polonium, which has a whole bunch of empty space. And we have to account for all that empty space. That's going to decrease the density of polonium. And so the volume here is the volume of the unit cell. And so the mass is just 209, right? U. The volume is A cubed. But we don't know what A is, but we do know what R is. And so the density is going to be 209U divided by 2R quantity cubed, because A is 2 radii. And the radii are in picometers, so that's 2 times 168 picometers quantity cubed. But the units are going to be wrong, because this is going to be in terms of U per cubic picometer. I don't want U per cubic picometer. I want grams per cubic centimeter. And so, well, that's easy. That's just dimensional analysis. And so we're going to convert U to gram. Do you have the conversion factor memorized for U to gram?
1.6022. 6.6.
Yeah. I like that one better. I like 1 gram is 6.022 times 10 to the 23rd U. It's easier to remember because it's Avogadro's number. And so that gets grams, and then we're going to go picometers to meters and the meters to centimeters. So how many picometers are there in a meter? So we go, what is it? There are 1,000 millimeters, 1,000,000 micrometers. What's after micro? Nano, 1 billion nano, and a trillion pico. And so there are trillion picometers in a meter. So I'll just say 1 times 10 to the 12 picometers per meter. And then we know that there's in 1 meter there's 100 centimeters. But we have to remember we have to cube these. This is cube, from way back when we were doing dimensional analysis. Unfortunately, I don't have my calculator, so can somebody punch this out and see what the theoretical density is?
Yeah. 9.14.
9.14.
Yeah.
Oh, so it's not terribly dense. Well, that's because it doesn't pack very efficiently. It doesn't pack like gold, right? It's a very heavy atom. 209 U is a very heavy atom.
Packs like styrofoam.
But yeah, 9 point, what is it?
9.14. That's for 3
Grams per cubic centimeter?
Yes. So that's 3 significant figures, right?
Yeah. 3 is pushing it because 209's uncertain.
Yeah, say 209 is a rough estimate.
Yeah. So that's a rough estimate of the theoretical density.
So that right there is a rough estimate.
Yeah. So it's not as dense as lead even though the atoms are much heavier than lead. It's just the packing efficiency is low. All right. But, you know, we can make ionic structures from this. So the ionic structure we made was cesium chloride. Because the cesium, you know, cesium's a big cation. It fits perfectly in there. Like that. Do you see how perfectly that fits? Cesium chloride? But what if the atom were bigger? What if we try to add a colorless ball? Try to put the colorless ball in the center. Does it fit so nicely?
No.
No, it doesn't fit so nicely. So if I just squeeze a colorless ball in the center, do you see it kind of distorts everything? It doesn't pack together as nicely. Or what if I spit a tiny one? Do you know you have tiny ones? You have tiny pink ones and tiny blue ones. So if I take a tiny pink one, does that fit nicely in the center? No, it doesn't. It doesn't fit so nicely in the center. And the blue one, it doesn't fit so nicely in the center. But the green one fits perfectly in the center. Keep that in mind, because we're going to come back to that. Okay, now if I fit a colorless one in the center, then it totally distorts things. You see the colorless one in the center is like, it's expanded now. And actually this isn't correctly expanded. It expands so that none of the corner atoms touch anymore. So what we're going to do is we're going to build on the next page of the handout here. We're going to build not the cesium chloride, which we just did. We're not going to do the cesium chloride body diagonal. We're going to go to body-centered cubic. Body-centered cubic, we need template F in the full moon. So we don't have to disassemble this. So find template F. Align it on the full moon, and then we're just going to do the shaded area. Now we're going to have 3 layers. Layer 1 and 1' are the same. And so layer 1, 4 atoms on the corner. Actually, I don't. Okay, so I have a gap here. We figured out the relationship between RNA and a body-centered cubic. But anyway, this is going to be 2 times 183.85 U divided by A cubed. A is going to be 4 root 3 R cubed. And then we got to convert this to grams and to centimeters.
Grams and centimeters.
Cubic centimeters, yeah.
Yeah.
So can somebody calculate it? Body-centered cubic is the hardest one. Face-centered, which is the next one's easier. Body-centered cubic is the hardest one because the relationship between R and A makes it difficult. The triangles. We're going to add one rod. Add one more rod in the center and build one more atom in layer 2. And so do you see how I have mine set up here? We're going to add one more atom for layer 2. What that's going to do is it's going to seal up the hole. And so do you see you have a hole on the side of the unit cell? We're going to seal it up with one atom. Okay, what did we call the previous hole? The previous hole, which we fit the green atom fit perfectly in this previous hole. Remember that? What did we call the previous hole? Cubic hole. What do we call this hole? This is not a cubic hole and it's much smaller. What do we call this hole? No, not that. Not centric. You just look at this and what was the this is one of our molecular geometries that we learned. We didn't have cubic as molecular geometry, but this is one of the molecular geometries. In fact, it's the same molecular geometry as SF6. What was the molecular geometry of SF6? Octahedral. So take a look inside the hole. Do you see this is called an octahedral hole, and do you see why it's called an octahedral hole? It's surrounded by 6 atoms in an octahedral geometry. Do you see that? It's kind of tilted, but you can see it. There's 4 in the plane, 1 on top, 1 below. What color ball fits in there? The pink one's probably too small. Try to fit a blue one in there. Green one's too big, right? So try to fit a blue one in that octahedral hole and see if it fits. It's close. It's close. It needs to be a little bit smaller than the blue, but a little bit bigger than the pink. Pink one might fall out. Let's see if I can put a pink one in there. Yeah, pink one's going to fall out. And so an atom between a blue and a pink should fit in there nicely, don't you think? In fact, it should fit in there perfectly. If we put a blue one in there, it'll expand it. And then things don't touch like they once did. Okay. But anyway, the point is, octahedral hole is smaller or bigger than a cubic? Smaller. Smaller. Good. Okay, now we're going to move on from body-centered to face-centered cubic. So page 27. Template C. So look for template C, and I'm going to disassemble one of these. I need to disassemble the half Yeah, half million. We're gonna need 9 rods. Or actually, not 9 rods. What are we gonna need? Just put rods in the holes with the circle. Okay, layer 1 you can see is going to consist of 5. Coalesce balls. Actually, we're going to need a rod in the center, aren't we?
Yeah.
Yeah, we are. And so we'll put, basically layer 1 is 4 rods on, 4 balls on the corner and 1 ball in the center. Now we're going to need 4 balls on the sides of the square. And so I'll put 4 balls on the sides of the square for layer 2. And then layer 3 will be a repeat of layer 1. What's that? Yeah, 1 prime is just repeat of 1. So layer 3 is going to be 5 balls, 4 on the corners, 1 in the center.
Now you do corners, and you do sides, and then you do corners again. Like this.
You mean our mic?
Yeah, 5 on the first layer, 4 on the second layer, 5 on the third layer. Do you see that the packing is very efficient here? The first thing we're going to look at is this. If you look at the first layer, is that packed very efficiently? It doesn't look like it, right?
Square is terrible for like machining.
Nor does the second layer. It looks like there are a whole bunch of gaps between the balls on the first layer and the second layer and the third layer. However, tilt this. So stand up the cube on one of the corners. And so tilt it so it's standing on a corner. Now look at the layers. The bottom layer, there's 4 layers. Do you see it? The bottom layer consists of 1 atom. The top layer consists of 1 atom. Do you see that? And so you're going to pinch the cube on opposite corners and arrange it vertically. So 1 corner stands on the bottom and 1 corner stands at the top like this. So pinch opposite corners and then tilt it vertically. And now you have 4 layers. Do you see it now? Okay, let's take a look at the second layer. So move the third and the fourth layer up, and then look at how the atoms pack in the second layer, looking down at it. So what I'm going to do is I'm going to push the top 2 layers and then look at that. Do you see how well they're packed? Do you know what we call that? We call that closest packing. That's called closest packing. Take a look at the third layer. Do you see that? That's also closest packing. And so this is called closest packing. Now, this is called cubic closest packing because cubic closest packing packs A, B, C, A. So look at layer 1's called A, layer 2 is called B, layer 3 is called C, and then we're back to A because A superimposes the first layer. There's another type of closest packing. It's called hexagonal closest packing. Hexagonal closest packing goes A, B, and then goes back to A. And so what we did was, if you look at this, and you look at the atoms, what we did was we rotated the 3. Remember there's 3 on the bottom and the 3 on the top? We rotated the 3. In hexagonal, you don't rotate the 3 on the top. The 3 on the top stay the same. So this is called cubic closest packing because the unit cell forms a cube. And so when we stand up the cube, we see the repeating unit here. And cubic closest packing is also called face-centered cubic. So CCP is the same thing as FCC.
So the second and third layer, that's made up of 6 balls, and they're just.
Yeah, no, we can make more. I mean, we can make a lot more balls. But the second and the third layer are, yeah, they're made up of 6 balls, closest packed.
So in a way they're like the same.
Yeah, it's the same. If we put more balls around there, then we'd see that the coordination. Can you look at the coordination number and tell me what the coordination number is? It's kind of hard to tell what the coordination number is. But this is how you do it. Pick the ball in the center of the face of the cube. How many balls is that touching directly?
8.
Okay, it's touching 8. 4 below, 4 in the plane. And then you add one more layer, and it's going to touch another 4. And so the coordination number here is 12. Just like gold. In fact, this is gold. We can calculate the theoretical structure of gold. This is the most efficient packing. If we look at the void spaces, there are 2 types of void spaces. There's a void in the center. Is there anything in the center of this? So lift up some atoms and see, is there anything in the direct center of the cube? No, it's empty. What kind of void is, what kind of hole is that in the center? So look at how many atoms it's coordinated to. And that center one is called a... Actually, we already covered it. It's an octahedral hole. And so in the direct center of this is an octahedral hole. Look at the middle of the side here. If you look at the middle of the edge, do you know what type of hole that is? So if we were to fill in this hole with atoms, what kind of hole will this become? Octahedral also. And so the one dead center is octahedral, and each gap on the side is also octahedral. And so how many octahedral holes do we have? We have one in the center, and then we have one on each side. So a lot. Yeah. Okay, now lift a corner atom up. When you lift a corner atom up, do you see there are 3 atoms below it?
Yeah.
And that forms a hole. Drop the corner atom, and what do you call that hole? That's not trigonal. Trigonal is if there wasn't a corner on there. It's not cubic. It is... What has 4 things coordinated to it? Coordination number 4 is tetrahedral. This is called a tetrahedral hole. Okay, the first thing we're going to do is we're going to see what fits an octahedral hole. So what you could do is you could lift off the center top and then drop something right in the center. What looks better, a blue one or a pink one? Blue one. So let's drop a blue one right in the center there. Do you see it fits pretty nicely in the center? And then we could put the center one back on top, and that blue one's nicely fit. It's not, maybe it's not perfect. Get a blue one and put it in the side of the cube, which is also an octahedral hole. And do you see the blue one fits nicely in the side there?
Yeah.
In fact, we could put a lot of blue ones here. One blue one directly in the center, and then how many sides are there on a cube? 4 plus 4 plus 4, 12. Does it make sense? So the blue ones fit nicely there, don't they?
Yeah.
If we called the colorless ones chloride and the blue ones sodium, do you know what we just built? Sodium chloride. And so one way of thinking about sodium chloride is it's a face-centered cubic lattice of chloride ions with sodium ions in the octahedral holes. We're going to build sodium chloride later, but essentially this is it. Okay, let's remove the blue ones out of there. And then we're going to put something in the tetrahedral holes. And so let's try to put a pink one in the tetrahedral hole. You have to be careful with the tetrahedral hole because the pink one doesn't go on a rod. The pink one just sits in the little nest of 3. Do you see the pink one fits perfectly in there? Now, how many of those little holes are there? How many tetrahedral holes are there in this cube? 8. There are 8 corners. If we put a pink one in each of those holes, do you know what we just made? Zinc sulfide. The zinc would be the pink, and the colorless would be sulfide. That would be zinc sulfide. Okay, let's get rid of the pink one. All right, so the first thing we're going to do is count how many atoms are in the unit cell. We know what the coordination number is. We already did that. This is face-centered cubic or cubic closest packing. So it's FCC, face-centered cubic, or CCP, cubic closest packing. Coordination number is 12. How many atoms per cell? So somebody figure that out for me. How many atoms per cell? Remember, the cell is going to go to the center of the corner atoms. Would it be 4? Is that what other people got? So we're going to have 1 atom from the corner, and then how many sides, how many faces do we have? We have 6 faces, and each face atom is shared with how many cells? 1 other cell, so 2 cells per face. And so that's correct, Tristan. It's 4 atoms per cell. So 8 corners times 1/8 of a corner per cell, and then 6 face times 1/2 atom per cell.
What about the one in the center?
The center's empty.
Oh, the center is. No.
So that gives us a total of 4 atoms. The triangles are a bit easier here. Look at where the atoms touch. Do they touch along the edge of the cell, the side? No. Where do the atoms touch? On the face. And so this one's a lot easier. then the body-centered one here. Since the atoms touch along the face, we'll just look at the face here. And so this is length A, this is length A. The atoms touch along what we call the face diagonal. And so the face diagonal is going to equal 4R, and that's going to equal how many A? So this is 4R, R, there are two R's in this, and one R here, 4R. And this is an equilateral triangle, and the hypotenuse of the equilateral triangle is equal to, we actually did this earlier, square root of 2A. Okay, so calculate the theoretical calculate the packing efficiency. This is the highest packing efficiency that we're going to get. So we had like 50 something percent, 60 something percent. What is this one? This is actually 68% was the last one. That's pretty good. Let me know when you get it. Packing efficiencies if we fill up the holes, which we're going to do in the next one. So basically, the biggest hole is going to be called what? Cubic, followed by the next biggest is? No.
It's not tetra.
No. Octahedral, and then?
Tetrahedral.
Then tetrahedral. And then there's one more hole, which is trigonal, but it's not something we're going to worry about. But what we can do is we can figure out what type of hole the cation goes in based on something called the radius ratio. And so this is a radius ratio. It's a rule. It's not a law, and it depends on the, how big the hole is. And so you see. Only the smallest cations can go in the tetrahedral hole. And so if you take the radius of the cation divided by the radius of the anion, we get the radius ratio. So if we get a radius ratio falling between 0.225 and 0.414, then the tetrahedral hole is occupied in the FCC. A little bit bigger cation is going to occupy the octahedral hole in the FCC. But the biggest cations have to go into a cubic hole, and that's going to be a primitive or simple cubic lattice. And so the radius ratio tells us a lot of what to expect in an ionic solid. So what we're going to do is we're going to look at something with a radius ratio of between 0.4 and 0.7. You don't have to memorize this. This is just to get a feel. And so we're going to get a cation. In fact, the blue cation fits here. So this is the pink cation, this is the blue cation, this is the green cation, essentially. And so the blue cation is going to fit nicely here. So what we're going to do is we're going to build it. And we're going to build it using page 33. And now we have to use the plastic spacers in the Ziploc bag. The plastic spacers are to scale. So you'll see that we're going to need the plastic spacer that's 7.4 millimeters in length. And so I don't even know if I have enough. I don't even have enough. You don't either?
I don't have any.
You don't have? It's in this plastic Ziploc bag. Who? Well, what we're going to have to do is we're going to have to get a pair of scissors and make our own using one of the long. If you don't have enough, take a pair of scissors. How many are we going to need? We're going to need 1, 2, 3, 4. 4. We only need 4 of them. We might be able to do, I have 2 of them. We might be able to make do with a little bit longer one. But do I have some scissors here? I don't have scissors. I'll have to get some scissors from the stockroom. Hold on a minute. We can figure out the length of the edge of sodium chloride by looking at how many radii there are. And so the big ones are chloride. How many radii for chloride? 4. So the big ones are, is it 4? No, it's not 4. It's 2. So the corners, this is one radius of chloride. This is the other radius of the chloride. And then there's one diameter of sodium, which is 2 radii. And so there are 2 radii of chloride and 2 radii of sodium. So A is equal to 2 times the radius of chloride plus 2 times the radius of sodium ion. So all we need to know is what is the radius of the sodium ion, what is the radius of the chloride ion? Well, that's easy to find. So let's go ahead and find that. That's the van der Waals radius. Ionic radii. Why do they do nanometers? Is so weird. Here it is. We're just going to use this. The ionic radius of sodium ion is 1.02 angstroms. How many picometers is that? 1.02 angstroms is how many picometers? 102 picometers. So the sodium ion is 102 picometers. What's the chloride ion? They do nanometers here. 0.181 nanometers is how many picometers? 181. 181. Nobody does nanometers because you have to have the 0 point. And so 181 nanometers. Or no, sorry. 0.181 nanometers is 181 picometers. You're trying to find the packing efficiency.
I got 8 numbers or something.
This is actually a homework problem.
Oh boy.
Chapter 12. I think, or the density. I can't remember. Maybe it's the density. We're going to also calculate the theoretical density of sodium chloride. It's an advanced problem.